Okay, we can get started. Welcome to CS229R, Algorithms for Big Data. I put some logistical information on the board there. If you're going to email, if you want to email me or the TF is right there. That's Yaroslav. Please email this address. It's all on the class website. It still goes to our inboxes, our main inboxes. It's just it gets auto-tagged in the right way, so I won't lose track of it. So I recommend emailing us that way. I'll spend just a couple seconds talking about logistics before I really start. So lectures will be recorded. We have a videographer with us in the back. And there will be links on the course website to videos. Prereqs, undergrad algorithms, probability, linear algebra. Grading, we're going to have P-sets roughly every week and a half. If you look at the fall 2013 website, we're going to have probably less P-sets this time around. Give you more time to think about the final project. Scribing, can I get any volunteer to scribe today's lecture? So scribing means you write notes on the lecture and then you email it to the staff email address by 6 p.m. the next day. So I think today is a particularly light lecture to scribe because I'm spending time at the beginning talking about logistics, but any volunteers? And everyone has to scribe at least once if you take the class. So. If you think you're going to take it, no scribe volunteers. Okay. Okay, so that's okay. So we have one. Okay, good. So, oh, and also all the dates of the class are on the website. If there's a particular date you want to scribe, you should email us, and then we'll list you for scribing that date. And it's first come, first serve. So take the spot that you prefer early. There's a final project and a presentation. Combined is half your grade. Presentation is about 10%. Final project is 40. And you can work in teams of up to 3. And also, every student is expected to help grade 1 P-set with the TF. OK. So what is this class about? So it's about algorithms for big data. What do I mean by that? I mean input data that's, say, so large that the traditional way of analyzing algorithms you learned in, say, undergrad algorithms is, insufficient. So, for example, maybe you don't have enough memory to store the input even, right? So you have one pass over the input and you need to compute something. Maybe it fits on your computer, but it doesn't fit in memory. You have to use disk, and then you have to take into account that disk IOs are much slower than memory accesses, et cetera. Okay, so let me give an overview of maybe 5, 6 things that we're going to talk about in this class. So one is sketching and streaming. So this is a topic overview. And also I sent a paper going, yeah, it's over there. Okay, so make sure that before you leave this classroom, you sign up for the class. Or you sign up for me to put your name on the course mailing list. Okay, that's in the back there. It's going to pass around. So topic overview 1, sketching and streaming. Okay, so what do I mean by this? What is a sketch? What do I mean by streaming? So sketching, so a sketch C of x, with respect to some function f, okay, is a compression of the data x. So x is the data, okay, and a sketch of the data is the C of x. And the sketch is a compression with respect to some function f if it allows me, computing or approximating let's say f of x given access only to C of x. Okay. And sometimes we care about, sometimes f has 2 arguments. So, we want, or multiple arguments. We want f of xy given C of x and C of y. So just to locate this in reality somehow, let's look at the second bullet here. So maybe you have some input data and I have some input data, and we want to compute some similarity measure of these data bases, okay, or of these data items. So one way is I can just send you my database, and then you can compute locally the similarity measure, or vice versa. But imagine that these are really big data sets, okay? And I don't want to, it's expensive to send that much data across the wire. So rather what I'll do is I'll locally just compute the sketch of my data, right? And then send the sketch to you, which is something much smaller. It's a compression. Did I say it's a compression? So it's a compression. I didn't write it, but I said it. So C of x is much smaller than x is. And then given the sketch, you can compute the function, right? The similarity measure, let's say. Okay. And to give a really trivial example, let's say that my data is a bunch of numbers and your data is a bunch of numbers, and f is their sum. Okay. The sketch I can do is just locally compute the sum of all my input data and then send you the sum, which is a lot smaller than sending you my entire list of numbers. That's a trivial example, but you can do more sophisticated things in Sketchland. Okay, so questions about what sketching is? Okay, and then streaming. Well, the way you can think about it for now, anyway, is you want to build a sketch to maintain, let's say, our sketch C of x on the fly as x is updated. Okay, so my list of numbers is growing. I keep seeing more and more. I can keep a running sum. Okay, the running sum is a streaming algorithm. So it maintains the sketch of the data as the data is updated. Okay. And these kinds of things appear in a lot of places. So for example, say you're a router and you're monitoring network traffic, right? And you want to be able to sketch network traffic so that AT&T can later come and query about the traffic patterns, find anomalies, et cetera. Okay? Or compare traffic patterns at two different locations in the network. Feel free to interrupt me with questions. Okay. Good, so that's sketching and streaming. That's the first topic we're going to cover in the course. Another topic we're going to spend time on is dimensionality reduction. Okay, and it's what the name says. So my input, my data is a bunch of high-dimensional vectors. So data is high-dimensional. Okay, and what dimensionality reduction lets you do is map your data transform your data into a low-dimensional version such that whatever computational problem you're considering, okay, if you solve that computational problem on the lower dimensional transformed data, you can then somehow lift that solution to the original data. And the point is that since the data is now low dimensional, algorithms will run faster on it. Presumably, the running time or resources required by your algorithm depends on the dimension of the input, right? The bigger the dimension, presumably, the slower or more space, et cetera, it takes. So by first hitting it with dimensionality reduction, you can speed that up. So, speed up clustering algorithms, nearest neighbor search in high dimensions, et cetera. Nearest neighbor, say, I have a database of images. Images are really just high-dimensional vectors, right? Every pixel is a dimension, and the value of that dimension is, say, the intensity of the pixel or something. Okay, and I have a database of images, and a new image comes, and I want to locate someone in my database who's close by, like I want to auto-tag pictures on Facebook or something. Okay. So dimensionality reduction is a way of handling such high-dimensional data. We're also going to talk about it's related to, well, many of these things that I'm going to write down you're going to see in the course are actually quite related. The tools that we develop in streaming and sketching are going to be related to things that we do in dimensionality reduction, which are going to be related to the next thing I write, et cetera. So we're going to look at some things. This is not a machine learning course, but we're going to look at some large-scale machine learning problems, more from the algorithm side. Like machine learning people want to solve some problem in their algorithms, and then how do you speed that up? So for example, regression problems, large-scale regression problems. We collect a bunch of data which looks like, the ith data item looks something like bi is equal to f of xi plus noise, or let's say f of zi plus noise. Okay. So we imagine that there is one variable b, which is somehow a function of a bunch of other variables, which I'm calling z. And I want to learn the relationship between this variable and these variables. Okay. So that's regression. And I imagine that I get a bunch of observations, possibly with noise. And based on that, I want to basically recover f. Or there's noise, so you're not going to recover f exactly, but you want to recover, say, f tilde, which is close to f. Okay. And from the statistics side, kind of the more data you see, the closer you should be able to get. With some good probability, f tilde will get closer and closer as you see more data. So a little linear algebra, maybe some of you have heard of the case, linear regression. Where f of z is, let's say, it's a linear function. It's some, let's say, x dot z, maybe plus a constant term or something. And now really the parameters here are, this vector x. You want to recover x, right? And from statistics, we know that if the noise is, say, Gaussian noise, you know that a popular estimator to use, or one that is provably optimal in some sense, is least squares. The maximum likelihood estimator, I guess, is the right word. So you said z tilde, or z least squares, is the minimizer. X least squares, sorry. X least squares is the minimizer. Of zx minus b L2 norm squared. So this is least squares regression. Okay? And let's say you have a really huge regression problem. So can you raise your hand if you've seen least squares regression? Raise your hand if you've never seen least squares regression. Okay, so some people haven't. Okay. But I'll just tell you that this has a closed form solution, which looks something like, let's say z has full column rank, z transpose z inverse z transpose b. Okay, the rows of z are the zi's. The z is a matrix here, the rows of which are the zi's, and b is the vector of the bi's. We'll get into this more later in the course, but the point is, if you want to solve, say, least squares regression, it involves some big matrix multiplication, which is expensive, right? The more data you have, the more data you collect, the more expensive this operation is. And we'll see techniques that allow you to solve problems like, well, least squares regression in particular, to get good least squares answers much faster than just doing this, which is the thing that you would learn when you first learn least squares. Okay, and we'll also see, so at least linear regression was just one example, but there are a bunch of other examples. So for example, some other forms of regression. not just linear regression. PCA is another thing. Principal components analysis is another thing we're going to talk about later in the course. Matrix completion is another thing we're going to talk about. It's often called the Netflix problem, where you're given a big matrix, let's say users of Netflix and movies, and then people rate movies. Okay? And based on the ratings you collect, which is very sparse, right? Most people don't rate every movie. You have very few ratings. You want to infer what the other unknown ratings probably would be, so that you can do product recommendations. Okay, so we're going to talk about some of that. We're also going to talk about compressed sensing. And the idea here is compress or even cheaply acquire, depending on the scenario you're in, high-dimensional structured signal. Okay. So what do I mean by high-dimensional structured signal? So for example, take an image of this room, or a typical image. Okay. As I mentioned before, an image is really a high-dimensional vector, right, indexed by the pixels. So if you have 1,000 by 1,000 pixels, this is a million-dimensional vector. Okay. And in the usual basis that we use, right, if you write down the usual basis for a million-dimensional space, the picture probably is not sparse, right? By sparse, I mean mostly 0. Okay? Most images in the picture, well, unless you take a picture of like a black room or something, most pixels will have some intensity in them. But there's something called the wavelet basis, okay? And pictures are usually sparse in the wavelet basis. And I won't tell you what the wavelet basis is exactly, but the basic idea here is, yes, in the standard basis, pictures are not usually sparse. But if you look at any pixel and look at, say, the pixel's intensity versus the average of its neighbor's intensity, okay, those differences are usually pretty small. Images don't change very quickly from pixel to pixel, okay, unless your image is random noise, okay. So there's a basis transformation you can do where most images actually are sparse. So really you have a high-dimensional signal which is sparse in some basis. Okay? And because it's sparse, you expect that you should be able to compress it. Maybe lossy compression. It's not perfectly sparse, right? You're not exactly your neighbor, but you're very close. So there's some lossy compression. And then given the lossy compression, you want to be able to decompress, right? So this is, for example, how JPEG exploits the fact that images have this structure, that they're sparse in a certain basis, right? So example applications, JPEG, or just image compression. Or MRI. Okay, so the MRI machines are also taking some measurements, okay, which are sparse in a certain basis. And kind of if you can, so here it's compression, here it's cheap acquisition, right? So basically, the longer your body stays in the MRI machine, the more measurements the machine can take, okay? And if you can take few measurements, okay, that means that you spend less time in the machine, which is, ideal, I guess, especially if the person is, say, a little kid and you can't get them to stay still. Okay. And I should say, usually when people say compressed sensing, they mean using linear measurements. So this is a vector in high dimensions, and we want to take using few linear measurements. Okay. I'll just say 2 more, and then I'll start doing stuff. Okay. One other thing I said is external memory model. This is what I was saying earlier, where when you took CS124 or whatever other undergrad algorithms course you took, you usually measured efficiency of an algorithm in terms of number of instructions that it executes on the input. right? But this is a different model for measuring efficiency. So measure disk IOs instead of number of instructions. Or you can measure both and try and be good in both at the same time. And the reason is, if you compare, let's say, most computers, if you compare the time it takes, in seconds or in fractions of a second to touch a cell in memory in RAM versus to seek to some random position on disk, okay, not flash, but let's say an actual magnetic disk, it's about 6 orders of magnitude difference between those two, okay? So as long as you're not doing anything too crazy with number of instructions, kind of a first order proxy is I should really minimize disk IOs. And maybe condition on that, I'll also want to minimize number of instructions. But I'm going to focus my attention on disk IOs. And random seeks are expensive. And the idea here is seeking to a random location on disk takes time. But then once the head is already there reading, I can, if I spent some milliseconds seeking to a random position, I might as well spend another millisecond or so reading the next few locations sequentially after that location, right? Basically to amortize against the seek cost, the random seek cost. So the model here is I have an infinite disk divided into blocks. Just think of a tape that goes on forever. Blocks of size B. Okay. And I also have memory, which is finite. It's divided into pages. Size B, and there are, let's say, M over B pages. So memory in total can hold M data items. Okay? And if the data that I want to read is in memory, or if the value I want to write is in memory, I can just simply read or write it for free. Okay? But if there's a location that I want to access that's not in memory, then I have to fetch it from disk. That costs me 1, and put it into memory. And memory might be full, so I also have to choose a page to evict from memory to disk. Okay, and here I want to minimize basically the number of times I have to go to disk. Okay? So there's this parameter B as well as the input size of the data, let's say. And something that you might have seen that was designed for the external memory model is, say, the B tree. Have people heard of B trees used in databases? Maybe some people have. If not, you'll see it at some point in this class. Okay, so that's external memory model, and then time permitting, we'll also maybe spend a lecture or at most 2 on other models, such as MapReduce, et cetera, other models, newer models for handling big data. Okay, good. So this was just an overview of the things we're going to see in this class. That about does it. So now I want to really start and show you your first kind of cool streaming algorithm. So questions about anything? Is the paper still going around to sign up with email addresses? Okay, it's somewhere over there. Okay, great. So streaming, so back to streaming. So we're going to look at a problem called approximate counting. And I think this, as far as I'm aware, this paper really is the first streaming paper. When the author wrote it, people weren't talking about streaming yet. He did it because, well, so what's this problem? So this problem is there are a bunch of events that happen. You're sitting here waiting, a bunch of events come, and someone asks you, okay, how many events have there been? So an event might be, I'm a website, and every time someone visits my page, that's an event. Okay, or I'm a router, a bunch of packets get routed through me. Each time a packet comes, that's an event. Okay, so someone asks me, how many events are there? Okay. And he wrote this paper in the 70s. Actually, his son is a professor down the road at MIT. This is the father. So he wrote this paper. Okay, so what's the trivial solution? Suppose that there are n events, right? And I'm just asking you how many events are there. And what my goal is to minimize space. I'm imagining that I'm a very space-bounded device. Okay, so I want to minimize space. What's the most straightforward solution? If there are n events, how much space would you use, and how would you do it? Yeah.
Log n, just sum them up as they happen, store in the counter.
Yeah, log n bits. You just store a counter, right? And every time you see an event, you increment the counter. Okay. Can you beat log n bits? Can you solve this problem in less than log n bits? No takers? All right. Okay. If the promise I give you is, if all I tell you is the final answer is somewhere between 0 and n, okay, now use at most log n bits for this problem. Then, yeah.
Well, you could store
An order of magnitude more cheaply.
Yeah.
How?
Well, the order of magnitude is only up to log n. So you could store the order of magnitude in log n.
So I want to know exactly the number of events, right?
You want, okay.
I want, yeah. Oh, yeah, good point. Okay, so I wrote approximate counting. So for exact counting, okay, sorry. For exact counting, can you beat log n? And the answer is no. So, okay, so, easy solution is counter log n bits, where n is the number of events. Again, you can't beat this with an exact solution just because of the pigeonhole principle, right? If you're using less than log n bits, then how many? Let's say you're using t bits. There are only 2 to the t-bit strings, right? Which by the pigeonhole principle means that there are 2 distinct numbers between 0 and n, which are getting mapped to the same state of your algorithm. So on one of those, you're wrong. Okay. But yes, as you were pointing out, if it's approximate counting, this is optimal for exact counting. Okay, so approximate counting want to output, let's say, an n tilde such that, so we're going to look at a randomized approximate algorithm. Want to output an n tilde such that the probability that n tilde deviates from the true n by more than epsilon n is at most delta. Okay. So at the beginning, someone gives me 2 parameters, epsilon and delta, and they say, design an algorithm for me which can give me this kind of guarantee, and I want you to use as little space as possible. For now, think of epsilon as like, let's say, a half or a third. I want to know the answer to within a factor of 2, and I want to work with 99% probability. Okay. So yeah, I guess you were saying before, I only need to, what's the lower bound for this problem that you were about to say? Well, forget about the randomness. Let's say it's a deterministic algorithm, and it has to know the answer up to a factor of 2.
So that would be log
log n, right? Because you really only need to know. You can round the answer to the nearest power of 2, and that's still a valid solution. And how many distinct powers of 2 are there between 1 and n. There are log n of them. So you really only need to remember which band you lie in. Which power of 2 are you close to? But there are only log n possibilities, so routing down a number between 1 and log n is log n bits. So you can't, at least deterministically, or even randomized, well, I won't justify it right now, you can't hope for better than log n bits. Okay? Right, it's the same pigeonhole argument. If you're using less than log n bits, there are 2 numbers from 2 different bands which are getting mapped to the same thing by pigeonhole, and your answer is wrong for one of them. It's not going to be a good approximation for one of them. So we can maybe hope for O of log n bits. Okay. So that's exactly what Morris does. Okay, so we're going to see Morris's algorithm is going to give us this kind of performance. Okay, so what's the algorithm? Step 1, initialize a variable x to 0. Okay. Step 2, for each event, increment x with probability 1 over 2 to the x. And 3, output 2 to the x minus 1. Okay, so every time we have an event, we increment with a certain probability. Imagine that my computer has a perfect rand function, which gives me a perfectly random number between 0 and 1. Okay, perfectly random real number between 0 and 1. We'll talk a little bit about de-randomization later in the class, how you might implement such a thing. That suffices for algorithms. And then when someone says, OK, what's n? How many events have there been? This is my n tilde. My n tilde, my estimate for n, is 2 to the x minus 1. OK, and just the intuition is supposed to be that x is sort of representing, log of n. Of course, x is a random variable, but we're hoping that x stays somewhere around log n. And I'm stealing this notation from a friend of mine where you drop the O from log. Basically, it means log base 2, and it also means, let's say, log of x is equal to log base 2 of 2 plus x. Okay, so it's never negative or anything. I don't want to keep writing. I don't want to have to deal with the fact that sometimes log of 1 is 0, and then if I divide by log, I'm dividing by 0, and things like that. Okay, so that's what log is, LG. So now we want to analyze this thing. Okay, and good. Now, I apologize, but maybe the next few minutes might bore some people here and not bore others. I just want to do a very quick probability review. And then I probably won't do any other reviews in lecture. But almost every algorithm almost every algorithm we're going to cover in this class is going to be randomized Monte Carlo, meaning it has some probability of failure, right? There's some delta probability of failure over there. And I really want to make sure that people are all on the same page. Okay. Actually, no, and even for the people who are going to be very familiar with everything I say, there's going to be one thing I'm going to say at the end, which I hopefully won't be familiar to anyone, at least in the form that I'm going to say it. Okay, so I'll try and keep it exciting. Okay, good. So before we analyze probability review, and it'll introduce some technique that we're going to see later in the course as well. So it's good to see it early and become a master. Probability review, good. So we're mostly in this class going to look at discrete random variables. X takes let's say value in some set S, some discrete set S, right? And expectation of X is the sum over J and S. J times the probability that X is equal to J, and there's the usual linearity of expectation. Okay. This is called linearity expectation. I'm not going to prove it. You can go read about it if you forgot. Okay, good. Other things I want to say, so there's Markov's inequality, which says that if X is a non-negative random variable, that implies that for all, let's say, lambda, the probability that X is bigger than lambda is at most the expectation of X over lambda. Okay, and then there are a bunch of other things that are just Markov on something. So there's Chebyshev. So now here, it says that for all lambda, the probability that X deviates from its mean by more than lambda, right? This is the kind of thing I like to know. I have a random variable like that one, like 2 to the x minus 1, and I'd like to know that it's concentrated around what I expect it to be, right? So what's the probability that it deviates by what it's expected to be by lambda? That's at most the expectation of X minus the expectation of X squared over lambda squared. So it's the expectation of the square, not the square of the expectation. And the proof is just probability that X deviates from its expectation by more than lambda is the same thing as X minus expectation of X squared deviating, being bigger than lambda squared. Just square both sides. And then now you do Markov's inequality. Okay. And depending on the community you're talking to, some people call everything Chebyshev. So you can put a P here or something. So I can take higher moments. I don't have to take the second moment, right? So this thing, by the way, if P is 2, it's called variance. But we could work with other moments as well, right? Okay, and then there's Chernoff. Which says, let's see, x1 up to xn are independent. And I know that xi is always in the interval 0, 1. And also define x to be the sum over I of xi. What it says is the probability that x deviates from its mean by more than, say, lambda times its mean is at most 2 times e to the minus lambda squared times its expectation over 3, for all epsilon between 0 and 1, or lambda between 0 and 1. Okay. I mean, you can go read about it. This is basically Markov all over again. So the proof, I'll put the proof in one line. There are details, which you can find on pretty much, well, you can Google it if you really want to. So, okay, so the key is really here. This is bigger than that if and only if this to the to the second power is bigger than that to the second power, or to the pth power. I can apply whatever function I want here, right? As long as the function is, I guess, increasing. Or it should just be the case that f of this is bigger than this if and only if f of this is bigger than f of that, right? So the f that I'm going to use is going to be some particular f. So probability that x is minus expectation of x is bigger than lambda expectation of x is at most, or is equal to the probability that, well, what you would do really is you would do the upper bound and the lower bound separately. So the probability that this is bigger is equal to the probability that e to the t x minus expectation of x is bigger than e to the t expectation of x. Okay, so my function f of z is e to the tz. So I apply that function to both sides. Right, and this is bigger than that if and only if this is bigger than that. And then you do Markov on this. And then you have to do some calculations. And then you also want to know that the absolute value doesn't deviate with high probability. So you also have to look at what's the probability that the negative is smaller than the negative of this. And then again, you do Markov, where you apply e to whatever on both sides. Okay, so you can find that. You can find proofs of this pretty much. You can find it on Wiki. Okay, this is a very standard thing. Okay, and I promised that I was going to show one thing that maybe people haven't seen. Do I really want to? Yeah, okay, so, I'll show it. Yeah, okay, let's do it. So maybe you've seen the statement, but maybe you haven't seen the proof that I'll show you, which will imply Chernoff, for example. So this is called Bernstein. Okay, so it says that, again, you have x1 up to xn are independent. And you have that, let's say the absolute value of xi is at most k. You also have that x is the sum of xi. And you also know that, let's say sigma squared is the sum over I expectation of x minus expectation of xi squared. So sigma squared is the variance of x. Then the probability that x deviates from its expectation, I use less than twiddle to mean big O, so up to a constant. E to the minus c, probably that it's bigger than, let's say, t. E to the minus c t squared over sigma squared plus e to the minus c t over k. Okay. So the Chernoff form that I wrote here is implied by Bernstein. Okay. I'll leave that to you to verify as an exercise. Basically, the point is that if k is 1, so this corresponds to k being 1, if k is 1, then sigma squared is at most the mean. Okay, so you can prove that to yourself offline if you want. And then if you just plug in t being lambda expectation here, and epsilon is less than 1, or lambda is less than 1, this term is dominated by this term, and this term will give you exactly that up to the constant. The constant changes. I guess there was a 3. Here I put some constant c. Okay, but Chernoff is implied. This form of Chernoff that I've written is implied by Bernstein up to constants. There's a difference when lambda becomes bigger than 1. When lambda becomes bigger than 1, Chernoff actually gives you something that's stronger than this. But then there's a better version of Bernstein called Bennett's inequality, which I forget about it. We don't really care right now. Okay, so I guess I'll prove Bernstein, and I'll prove it in a way that will be useful later in the course as well. Okay. So it's good to see a trick early. So proof. So I'm going to use a couple things. I'm going to make some notation. So the p norm of a random variable z is the expectation of z to the p to the 1 over p. This is a norm for p bigger than or equal to 1. That's a fact. Okay. So I can do triangle inequality, et cetera. It's a norm. Okay. And I'm also going to use something called Jensen's inequality, which says that f is convex implies that f of the expectation of z is at most the expectation of f of z. This is called Jensen. Good. So now let's prove Bernstein. We have to prove that inequality. The problem that you deviate by t is at most that. Okay. So it's equivalent to prove that sum over ixi minus the expectation of sum over ixi p, to prove that for all p bigger than or equal to 1, this p norm is at most up to a constant root p times sigma plus p times k. Okay, so forget about equivalence for now. Suppose I had a bound on the p norm for all p. P norms are really like pth moments, right? P norm is like a pth moment to the 1 over p. So really, this means I have a bound on all the moments. How might you go from having a bound on all the moments to getting that bound? How would you go about it, given something that we've already talked about in today's lecture? Any ideas? Yeah.
Markov and then the definition of E as the limit of P goes to infinity.
So Markov, oh, okay. So Markov on e to the something?
Yeah.
So, okay, but so here all I'm saying is I only know what I have is I have bounds on the p norms, and I want to go to that. So I will use Markov, but what I'm going to use Markov on is I'm going to do exactly this. I'm going to do Markov on the pth power, right? Because that's what I know. I know I have a bound on the pth moment of this random variable. So I'm going to use that bound and then apply Markov. Okay? And if you're telling me to prove that kind of bound, right, then p is going to end up being a function of t. Okay, so basically I'm going to do Markov. I'm going to optimize my choice of p to give the best bound I can as a function of t, sigma, and k. And if you do that with this as your moment bound, you will get that. So I'm not going to do it on the board. You're going to have a probability review kind of one problem on your p set, which is going to come out soon. You're going to prove that this kind of statement, a bound on the moments for all moments, is the same thing as that statement. So that statement, I should have said, there's a for all in both of them, right? So for all t bigger than 0. So the statement that for all t you have this deviation bound is the same statement as for all p you have this kind of moment bound. Okay? So one direction is Markov. Okay? And the other direction, you can also go from there to here. And you'll see it on the p set. Okay? So these are the same statement. Okay? So let's prove this kind of bound. Okay. So I didn't explain all the details, the calculations of why they're equivalent, but let's just take it as they're equivalent because you're going to prove it on the p set anyway. Okay, so let yi be identically distributed as xi with xi over all I and yi over all I are independent. So now we have two n random variables. X went up to xn and y went up to yn. Okay, and xi and yi are distributed exactly like each other. So then that implies that sum over I xi minus expectation sum over I xi. That's the same thing as, this is just a number, right? This is a number. And it's the same number as if I had written expectation sum over I yi, where this is the expectation over y. Right? Okay. And really, I mean, I could put the expectation over y here if you want. The expectation over y of this big thing. And now I apply Jensen. If p is bigger than 1, then absolute value to the p is a convex function. So I can pull this expectation outside and put it in the p norm. So this is at most sum over I xi minus yi p norm, where now this is over the randomness in both x and y. This is by Jensen. And now, notice that xi minus yi is a symmetric random variable. For any value t, it's equally likely to be t or minus t. So this is identical in distribution to sum over I alpha I xi minus yi p norm, where alpha I is just a plus minus 1 random variable, random plus minus 1. Okay, and now I'm going to use the fact that what I said was this thing is a norm. Oops, did I? Oh my goodness, that was terrible. I erased the thing I didn't want to erase. That's okay. So I said that this thing is a norm. So this thing is at most 2 times sum over I. Well, I can write it like this. Sum over I alpha I xi p norm plus sum over I alpha I yi p norm. Right? I've just used triangle inequality. But yi and xi are distributed the same way. These two things are the same. This is just equal to 2 times the sum of over I alpha I xi. which, now here's maybe a magic trick that people haven't seen before. This is equal to 2 times the square root of pi over 2 times the expectation over g of sum over I, alpha I, absolute value of gi, xi, where g is vector of IID Gaussians. Okay, so what did I do? I just multiplied by 1. The expectation of the absolute value of a Gaussian is square root 2 over pi. Just some number. It doesn't really matter. Look it up if you want. It's just some number. And then I just divided by that number on the outside. So I just multiplied by 1. And then now what am I going to do? I'm going to use Jensen and pull this outside of the norm. By Jensen, this is at most, forget about constants, this is at most sum over I of alpha I absolute value of gi xi. This is again Jensen. What's a random sign times the absolute value of a Gaussian? It's a Gaussian, right? Yeah, a random sign times the absolute value of a Gaussian is a Gaussian. This is equal to sum over I gi xi. Okay. I apologize if people, I guess I start off saying discrete probability. If people are not so, aren't used to working with Gaussians all the time, everything that you're going to need to know about Gaussians, I'll just say it as I do it. Okay, so you don't really, I won't expect you to know that much in the future. So what happens when you add up a bunch of Gaussians? What do you get? You get a Gaussian. And the variances add. If you add up Gaussians, you get a Gaussian, the variances add. So this is just a Gaussian. This is a Gaussian with variances, with variance basically sum of xi squared. I don't want to erase that algorithm, so I'll leave it. Okay, great. So great. So now you can say, now you can just prove it for yourself or look it up in a book. What's the pth moment of a Gaussian? Okay, so look it up in a book. Expectation of a Gaussian to the, let's say you have that some random variable z is a Gaussian with mean 0 variance 1, then the expectation of z to the p is equal to 0 if p is odd, and something like p factorial over, p factorial over p over 2 factorial 2 to the p over 2 if p is even, which this thing is basically O of root p to the p by Stirling's formula. Well, it's actually at most root p to the p. Yeah, you can prove to yourself it's at most root p to the p. Great. So that thing there, and if instead you have a Gaussian with variance v squared, then you multiply this by a v to the p, basically. Okay. So there what we get is that thing over there is at most square root p times the p norm of sum over I xi squared to the 1/2. Right? This is v. V squared, the variance was this, so the standard deviation is the square root. Okay. And this thing here, what you can say is this is equal to, by the definition of p norm, this is equal to root p times sum over I xi squared to the p over 2, or actually I can even say to the p over 2 to the 1/2. So if this thing, in general, notice that if you have a random variable z p norm, this is the expectation of z to the p to the 1 over p, which is the same thing as saying expectation of z squared to the p over 2, right, to the 2 over p to the 1/2. Okay, those are the same thing. And this is the p over 2 norm of z squared to the 1/2. So that's all I did. So the p norm of this is the same as the p over 2 norm of this to the 1/2. Okay, and this is at most root p times sum over I xi squared p to the 1/2. This is because p norms increase. Okay, and that's equal to root p times sum over I xi squared minus expectation sum over I xi squared plus expectation sum over I xi squared. Good. Let me also say without loss of generality, let's say expectation of xi is equal to 0 for all I. So if that's not true, I'll replace each xi by xi minus its expectation. Okay. And now I'll use triangle inequality. This is at most root p times sum over I xi squared minus the expectation, or sum over expectation sum over I xi squared plus sum over I xi squared minus the expectation. So I shifted all the xi so they have mean 0. So what's this thing inside of here? Yeah, sorry, it's variance. So this here is just a number. It's sigma squared. It's not random, it's a number. And I took it to the 1/2. So this is equal to sigma root p. So I'm getting close, right? So sigma, yeah, root p times sigma. Okay, plus root p times sum over I xi minus expectation sum over I xi squared. And using the same exact sequence of tricks as last time, replacing these with y's, putting in random signs, using Jensen, putting Gaussians in arbitrarily, all that stuff. This is at most sigma root p plus root p times sum over I gi xi squared. Right? You can artificially, right? You can symmetrize. You can replace these with yi's, pull the expectation of y's outside, put the signs, put the Gaussians, do all that stuff. Okay. And now this, right? This absolute value is at most, well, what is this again? This is a Gaussian whose variance is the sum of xi to the 4th, right? This is a Gaussian variance sum of xi to the fourth, but I know that xi is at most k. Xi is never bigger than k. So this is at most k squared times sum of xi squared. So at the end of the day, what I have is there. Right? So I have that thing. So let's say star. Star was sum over I gi xi p norm is at most up to a constant sigma root p plus k squared. So the variance is k squared. So the standard deviation is k squared times this. So the standard deviation is the square root. That's k. And there's another square root. So plus root p times root k times sum over I gi xi, p norm to the 1/2. Right, so now this is a Gaussian whose variance is sum over I xi squared. And I've pulled out the k squared. Right? But does anything look funny about this to you? Almost. I've bounded something in terms of its own square root. Right? So let's call this thing Q. This big O, this less than twiddle is hiding a constant. What I've shown is that Q squared minus C sigma root P minus C root P root K Q, okay, is less than or equal to 0. This is some quadratic in Q. So this is Q. So what it looks like is, it's, because the leading coefficient is positive, as Q goes to minus infinity, it goes to infinity, it goes down, and then it goes back up again. And I said that this thing is less than or equal to 0, which means that Q is less than the larger root of the associated quadratic equation. And if you solve that quadratic equation, you'll get that, well, you'll basically get what I promised. Okay, so I'm not going to do it. So this is, I guess I'll call Rudelson's square root trick, where when you want to bound p norms, you bound them in terms of their own square root by artificially inserting Gaussians and things like that. We're going to do it later in the course. So when we do it later, I want you to be, you'll look at it and say, oh yeah, that's just lecture 1. Easy stuff. Okay, so good. Okay, so good. So now that we've done that, let's actually go back to analyzing Morse's algorithm. Okay. So let me erase some of this and let me write one conclusion that we had before. Which said xi's are in 0, 1, independent. Let's say mu is the expectation of sum over I xi, which I'm calling x. Then the probability that x deviates from its expectation by more than lambda mu is at most 2 times e to the minus lambda squared mu over 3 for all lambda between 0 and 1. Okay. So good. Now let's analyze Morse. Okay, so Morris. So the plan is going to be, first we want to know that the expectation is correct. Okay. Then we want to know that the variance is small, so we can say that it's good with Chebyshev. Okay. So claim. So okay, first I want to say let xn denote x after n events. So claim 1, the expectation of 2 to the x is equal to xn is equal to n plus 1. So xn is a random variable. Sometimes we incremented, sometimes we didn't. And the proof is by induction on n. Base case, n is equal to 0. That's fine. So when n is equal to 0, we haven't seen any events. So x is 0. So 2 to the 0 is 1, which is 0 plus 1. OK, great. Now for the inductive step, let's say that it's true for n, and we want to show that it's true for n plus 1. The expectation of 2 to the x n plus 1 is equal to, okay, so we've seen n events, and now we're seeing the n plus first. So let's just sum over all possibilities of what the counter was after n events. So it's the sum over all possibilities j for what the counter was after n events times the expectation of 2 to the xn plus 1 given that xn is equal to j. So this is the conditional expectation conditioned on the event that xn is equal to j. So if xn is equal to j, what are the possibilities for what xn plus 1 might be? I'm sorry? Or j or j plus 1? What did you say again? J or j plus 1. So 2 to the xn plus 1 will either be 2 to the j or 2 to the j plus 1. So that thing is equal to the sum over all j of the probability that xn is equal to j of, well, it's equal to 2 to the j with probability 1 minus 1 over 2 to the j, right? Because that's how the algorithm works. It increments with probability 1 over 2 to the x. So this is, we didn't increment. And with 1 over 2 to the j probability, we do increment. So with 1 over 2 to the j probability, we increment, and it becomes 2 to the j plus 1. Okay. So this is equal to the sum over j going from 0 to infinity of probability that xn is equal to j 2 to the j plus the sum over all j probability that xn is equal to j times 1. This is 1, right? The sum of all the sum of probabilities of being anything is 1. It has to be something. What's this? Yeah, this is the expectation of 2 to the xn, which we said was equal to n plus 1. This is our inductive step. So this thing is equal to n plus 1 plus 1. So we've completed our induction. Okay, and that's great. So good. So we know at least, let me not erase that. We know at least this thing is giving us the right thing in expectation. But what we want is not just that it's right in expectation. We want we want that the probability that n tilde deviates from n by more than epsilon times its expectation by epsilon n is at most delta, right? That's what we really wanted. We want to say it's close with high probability. OK. So let's bound the variance. So remember, the probability that n tilde minus n deviates by more than epsilon n is at most 1 over epsilon squared n squared times the expectation of n tilde minus n squared. This is Chebyshev's inequality. This is Markov on the second power. This is one of the things we had in the probability review just now. Right? And if you look at n tilde is 2 to the x minus 1. So if you square it, you're going to need to understand the expectation of 2 to the 2x. Right? So this thing here is 1 over epsilon squared n squared times the expectation of 2 to the x minus 1 minus n squared. Right? So if you square it, you're going to need to understand expectations of 2 to the 2x. So claim, I don't have time. I'm not going to write down the steps, but it's another inductive thing. You can show, what are you going to get exactly? Yeah, you're going to show that the expectation of 2 to the 2xn is equal to 3 halves n squared plus 3 halves n plus 1. Okay? So I'm not going to do it on the board, but it's another inductive proof. It'll be in the notes. Okay, so Jungyu, when you send me the notes, I'll just add it in myself. Okay, so okay, good. So if you then put that into here, this implies that the expectation of n tilde minus n squared, you're going to get something like 1 half n squared minus 2n minus 1, which is always at most 1 half n squared. So now we know that this, so we have this implies that the probability that n tilde minus n is bigger than epsilon n is at most 1 over epsilon squared n squared times 1 half n squared, or n squared over 2. And that cancels that. This is equal to 1 over 2 epsilon squared. Okay, so if a probability is bigger than 1, then that's kind of a useless bound. So let's say we want to succeed. Let's say we want to succeed with probability 2/3. Right? So if this thing is equal to 2/3, then epsilon is some pretty large constant close to 1. We're actually getting, we're getting some multiplicative error with 2/3 probability, but it's not like great. Okay? What if we really wanted to get 1 plus epsilon? Epsilon's a parameter, and someone says, I really want to get 1 plus epsilon. I really want epsilon as my error. How would you change this algorithm? How would you change this algorithm to get epsilon as your error? Any takers? Any other takers? Okay. Yeah, I'll run. So here's what I'll do. I'll say Morris plus is instantiate S independent copies of Morris and average their outputs. Okay. When you add a bunch of random variables, their variances add. but then you're averaging, so you're dividing by s. So effectively what this does is it decreases your variance by a factor of s. So this gets you, so this failure probability becomes 1 over 2s epsilon squared. Okay? So now if you want failure probability a third, if you want failure probability a third, how should you set s? Say it again? Yeah, so that thing there is equal to a third, or let's say it's less than a third for s bigger than 3 over 2 epsilon squared, which is theta 1 over epsilon squared. What if you wanted failure probability delta? What would you do? What would you change? Right? Or it's less than delta for s being bigger than 1 over 2 epsilon squared delta. Okay, so we have a minute left. So Morris plus, it's basically before your space was like log n. So we didn't analyze the space, but you're going to see on the homework with high probability the space is going to be at most log n. Now your space is 1 over epsilon squared times log n because you're repeating it 1 over epsilon squared times. If you want failure probability delta, it's 1 over epsilon squared times 1 over delta times log n. But there's a Morris plus plus, which gets you this delta more cheaply. Run t instantiations of Morris plus with failure probability 1/3, let's say. So s is theta 1 over epsilon squared. Output the median estimate from the s Morris pluses. And in the last, let's say, 30 seconds, I won't get to do the calculations. I'll put them in the notes. But why does this work? Well, Chernoff was going to be good for something in this lecture. Where's my better eraser? So run t instantiations, and I claim it works for t being something like log 1 over delta. So we replace the delta with log 1 over delta with log 1 over delta. And why does this work? Basically, it works because when does the median fail? Well, if the median fails, it means that at least half of the estimators had to fail. They had to give you a bad answer, right? But what fraction of the estimators, what fraction of the Morris pluses do you expect to fail? A third, right? You instantiated Morris pluses with failure probability a third. For the median to fail, it means that more than half failed, right? So what you do is let yi equal 1 if ith Morris plus failed and 0 otherwise. So we're asking what's the probability that the sum of yi is bigger than t over 2, which is less than the probability that the sum of yi minus the expectation sum of yi is bigger than t over 6, basically. Because this is something like t over 3, and we're bigger than t over 2, so we deviated by t over 6. This is going to be something like exponentially small in some constant times t by Chernoff. Okay, and t is like log 1 over delta times a constant, so this is delta. Okay, so this idea of averaging a bunch of estimators and taking medians is a useful way of doing things. Okay, so it's a general trick that you can do to turn a weak estimator into a very strong one with high probability, and you'll see more of it in the course. And for more specifically for approximate counting, there's something you can do better, and you'll see that on the first p set. Basically, instead of using 2 as the base, you'll use like some parameter as the base, and if you choose that parameter very well, you can get even better bounds. Okay, so that was lecture 1. Thanks.